Okay, on the rest of these problems, I'm going to not spend time on calculating derivatives. I'm going to assume that you know how to do that. So that'll save me a little bit of time on getting through these. All right, let's look at number 3. A steel drum in the shape of a right circular cylinder is required to have a volume of 100 cubic feet. Find the radius needed to maximize the required material. Okay, so here's your drum. And basically, I started the problem over here on the right. We want to maximize the, minimize the area that we use, because that'll be the amount of material. Now, the area of this drum, the side material, the side of the drum, that material is what we're going to use. We're also going to need some material for the top and the bottom. Now, the top and the bottom is the easy part, because the area of the top is just a circle, so the top is pi r squared, the bottom is pi r squared, so the area of the top plus the bottom is just 2 pi r squared. The area of the side, though, what you have to do is, if you cut this cylinder straight down and then unroll it, you'll get a rectangle like I have here, and the length of the rectangle is going to just be the same as the circumference of the circle that makes the drum, which is, and the circumference of a circle is 2 pi r, and then the height of the rectangle is just going to be h for the height. So 2 pi r h would be the area of this rectangle. So total area would be 2 pi r h plus pi r squared. And so that's actually going to be our primary equation. Now, in order to eliminate one of these variables here, we know that volume equals 100. So volume equals pi r squared h. But since we know that should be 100, we know pi r squared h should be 100. This v shouldn't be there. So anyway, once from this we can solve for h and get h equals 100 over pi r squared. So now we can take this equation and we can replace h with 100 over pi r squared. And you can see I did that here. And so when I replaced h with 100 over pi r squared and simplified it, I got area equals 200 over r plus 2 pi r squared, which actually can be written as 200 r to the negative 1 plus 2 pi r squared. And then you take the derivative and you get minus 200 r to the negative 2 plus 4 pi r. Now, what we want to do is we want to set this equal to 0 and solve it, find the critical numbers. Well, what you can do is, to get rid of this r to the negative 2, just multiply it by r squared. So I'm going to multiply every term by r squared. When I multiply this term by r squared, it just cancels the r to the negative 2. 4 pi r times r squared is 4 pi r cubed, and then 0 times r squared is 0. And then you can solve this for r cubed. Just move the minus 200 over, and you get 4 pi r cubed equals 200. Then divide 200 by 4 pi, and you get 50 over pi. But now that's just r cubed. We actually want r, so I'm going to have to take the cube root of that to get r. So r is 1.17 feet. That's what I got on my calculator. And that's the radius that we'll use to minimize that particular area of that drum. Okay, now let's look at another one. Okay, this one says a rectangular field is enclosed on 4 sides with a fence. And fencing costs $3 per foot for 2 opposite sides and $4 per foot for the other 2 sides. Find the dimensions of the field that has area 730 square feet that would be the cheapest to enclose. Well, down here's my field, my rectangular field. To me it made sense to have the longer sides be the cheaper cost, $3, and the shorter sides be $4. So these sides are going to be W, and this side's going to be L. Okay, so my primary equation would actually be, I would take 2L, which is the amount of sides I'd use for the length, amount of fence for the length, and multiply it by $3 per foot. And then I take 2W, so that would be the 2 sides for the width, and I'd multiply that by $4 per foot. So basically that's going to give me 6L plus 8W. Now, I need to eliminate one of these variables. Well, that's where this 730 square feet comes from. So I know the area of this rectangle is 730 square feet. Well, area is length times W, so I know length times W is 730. So then I can solve for L in terms of W and get 730 over W. Well, then I can go back to my primary equation, and I get 6L, which L is replaced with 730 over W, and then this is 8W, and now I have it in terms of a single variable W. Now if you multiply this together, you get 4380, and instead of putting W in the denominator, I wrote it as 4380 W to the negative 1, and then plus 8W, and that's so I can take the derivative. Now when you take the derivative of this, you're going to get minus 4380 W to the negative 2 power plus 8, and you're going to set that derivative equal to 0. And just like I did a while ago, to eliminate that W to the negative 2 power, I can multiply each term by W to the positive 2 power, or just W squared. So if I multiply this by W squared, this term just turns out to be minus 4380. This term is going to be 8W squared. And then I went ahead and factored a negative 8 out of this so that I could get this to just be minus W squared. So I got minus 8 times 547.5 minus W squared. Now if you solve this, remember we set it equal to 0, so if you solve this, you get W squared equals 547.5. And remember, to solve that for W, you simply take the square root of that. So the square root of 547.5 was 23.4 feet. So that's my width on each side. And then to get my length, remember up there I had a formula, length was 730 over W. So I take 730 and divide it by 23.4, and that will give me the length of each side is 31.2 feet. And so the dimensions should be 23.4 feet by 31.2 feet to minimize the cost of the fencing that we use. Okay, another one here. This one here, I'm going to let you do most of the work, but one of the things I want you to remember here is that over here, the top of this box is empty. So, I mean, there's no top on this box. So basically what you're going to try to do is you're going to minimize the amount of material. Well, the material consists of the 4 sides and then the bottom. Well, the 4 sides, let's just drop down here. So what you want to do is you want to minimize the area. Well, the area consists of 2 sides that are length by height, and then 2 sides that are W by height. So that would be 2LH plus 2WH, and then a base, which is length times W. So that's your primary equation. But you're given that L is 2W. So if you know L is 2W, everywhere you see an L, you can replace it with 2W. So in other words, I can use these two formulas, L equal 2W, and then I'm also given that the volume is 52, so I know LWH is 52. So if I use these two formulas in conjunction with one another, I can actually figure out a way to eliminate L and H. So, read what I did here to see how I eliminated L and H. So I knew L was 2W, and then from that I could get that H was 26 over W squared. And then once I got that, then I could plug all that in, and I ended up getting an area of 104 over W plus 52 over W plus 2W squared. And those you can add, these first two can be added together, so you get 156 over W plus 2W squared. And I just wrote it with a negative exponent, and then I took the derivative, and I set the derivative equal to 0, and like I did a while ago, you can see to eliminate W to the negative 1, I'm sorry, to eliminate W to the negative 2, just multiply each term by W squared, and then solve this problem for W. And then you can go plug it back into those earlier formulas that we had to get the length and the height. Okay? And so that's how you do. Okay, so the next one says a page is contain 30 square inches of print. So here's my page here. The inner rectangle represents the print area. Now it says the margins at the top and the bottom are 2 inches. So notice I put a 2 here and a 2 here. And at the sides the margins are 1 inch and 1 inch. Okay, so what I want to do is I want to minimize the amount of paper used. So what I want to do is I want to minimize the area of this paper, X times Y. So I'm going to let X be the width of the paper and Y be the height of the paper. And I want to minimize X times Y. Now, but the problem is I need to eliminate one of these variables. So this is where the print area comes in. I know this print area in here, and let me Okay, I just wanted to adjust my picture a bit. This shaded area in here has to equal an area of 30 inches. But remember, if the dimensions from here to here are x, then the dimensions from here to here must be x minus 2 because there's margins of 1 inch on each side. And if the dimensions from here top to bottom are y, then the dimensions from here to here must be y minus 4 because there are margins of 2 on top and margins of 2 on bottom. Well, that gives me a way to represent the area, this print area. I can represent it by x minus 2 times y minus 4. And so here you can see I have x minus 2 times y minus 4 must equal 30. And then you can actually solve that for y and get y equals 30 over x minus 2 plus 4. And then you can go back into your primary equation and replace y. And so you get x times that expression. And then when you multiply that, you get 30x over x minus 2 plus 4x. And then when you take the derivative, first term you're going to use the quotient rule. The second term is easy. The derivative of 4x is just 4. So you're going to get the quotient rule here for the first term and then 4 for the second term. And then after you do the quotient rule, you're going to get minus 60 over x minus 2 quantity squared plus 4. And then I'll leave you to solve this. You just set it equal to 0 and solve it. And so basically you get 4 equals 60 over x minus 2 squared. And if you multiply everything, or you can actually just cross multiply and get 4 times x minus 2 squared equals 60. And then divide by 4, then take square roots. And then x equals 2 plus or minus the square root of 15. But 2 minus the square root of 15 is negative, so that wouldn't make sense. So x has to be 2 plus the square root of 15, which is about 5.9. And then remember, y was 30 over x minus 2 plus 4. So plug 5.9 in here for x, and you can get y is 11.7. So the total size of the paper should be 5.9 inches by 11.7 inches. There's another problem here. Freeze the video and then practice on this problem and see if you can follow it, and then just check your answer, and then you can restart the video when you're finished. I'm just going to briefly touch on elasticity, and I'll let you, to save time, you can read all of this. But basically, the formula that our text gives for price elasticity of demand, if you're given a demand function P equal f of x, then eta is a Greek letter, and that represents what's called the elasticity. And you basically would take your function P and divide it by x, and then on the bottom you would take the derivative of P with respect to x. And let me show you. Here's an example. Here's a demand function. Price equals 20x cubed minus 300x. So if I wanted to calculate this value eta, the top, I just divide everything here by x. So if you divide this by x, you're going to get 20x squared. Divide minus 300 by x, you're going to get minus 300. And on the bottom, you actually take the derivative of this to get the denominator. So the derivative of this is 60x squared minus 300. And so this is the function for eta. And then if you want eta at a particular value, like if you wanted to know what eta was when x is 0, well, if you plug 0 in, you're actually going to get a value of 1. And when it's 1, you get unit elastic. And then if you plug 10 in, you're going to get 2,000 minus 300 over 6,000 minus 300. And that's going to give you 1,700 over 57. And that's less than 1. And when the absolute value of eta is less than 1, it's called inelastic. Okay? And again, I don't want to spend a whole lot of time on this, but I did want to make sure I showed you how you calculate the elasticity given the demand function. And that's pretty much it on the optimization problems.